today's video we're going to look at chemical equilibrium, and we're specifically going to look at the equilibrium constant. So our learning intention is to discuss and complete calculations involving the equilibrium constant. So to begin, we must identify what the equilibrium constant is represented by, and it's represented by Kc. So throughout this video, we will be referring to the equilibrium constant as Kc. So here's a sample equilibrium reaction. As you can see here, we've got our reactants and our products, but beside it I have the Kc formula that we will be using, or the equilibrium constant formula. So first of all, the square brackets tells us that the concentration of the reactants and the products is measured in moles per litre. Products are always written in the numerator, or the top, basically, the top of the fraction. And reactants are always in the denominator, which is the bottom of the fraction. And the concentration of each of the species is raised to the power of its coefficient in the balanced equation. So basically, if I was to label this or shade it in A, B, C and D, the small ones here correspond to the coefficients in front of our balanced equation, where then the capital letters, these are the concentrations in moles per litre. And then to box it off, the reactants, they're on the bottom, and the products, they are on the top. So this is our equilibrium constant formula that we will use in our calculations. So the value of our equilibrium constant, or Kc value, will indicate whether the reaction has proceeded very much towards the products or whether there has been very little conversion and mostly reactants are left behind. So if Kc is very large, basically if it's a lot bigger than 1, the concentration of the products is large and equilibrium lies on the right, or equilibrium lies to the forward reaction is favoured. If the Kc value is very small, i.e. less than 1, the concentration of the reactants is large and equilibrium lies to the left, meaning that the backward reaction is favoured. If Kc is close to 1, then we can say that the concentration of the reactants and the products is equal. So the value of Kc is only affected by temperature. It does not change with concentration or pressure. So a change in temperature causes a change in equilibrium concentrations, which causes the equilibrium constant itself to change. Kc value is not changed by pressure, and this is because the number of moles of each species is balanced out by the change in volume. And finally, the units of Kc depend on the reaction itself. So here we have the Haber process again, but I want to write the equilibrium constant for this reaction. So I know that the equilibrium constant is Kc, and that's equal to a fraction. I know that the products go on top, so I'm going to have a square bracket here with ammonia in it, and that's going to be raised to the power of 2 because that's the coefficient in front of the ammonia. And on the bottom, I'm going to have N2, and that's raised to the power of 1, and then I have H2, which is hydrogen, and that's going to be raised to the power of 3. So that is the Kc equilibrium constant equation for the Haber process. So a very common question to come up in equilibrium is to calculate your equilibrium constant, or work with your equilibrium constant to calculate something else. And it's important when you're working with your equilibrium that you will never deal in grams. We must always deal in moles. So you must always ensure to convert units to moles. So always ensure to divide by the molecular mass when it is required. For equilibrium calculations, I tend to use something called the Rice method. So I have reaction, initial concentration, change in concentration, and concentration at equilibrium. And there's two types of questions when looking at the equilibrium constant. The first one is to calculate the equilibrium constant given some information on the concentrations, and the other is to calculate the concentrations given the equilibrium constant. So we're going to look at an example of both of these individually now. So the first calculation that we're going to do is we're going to calculate the equilibrium constant given some information on the concentrations. And to do that, we follow a series of steps. So the first thing we'll do is we will convert all given quantities from grams to moles, and you do that using your molecular mass, and we've said that already. The next thing you're going to do is you're going to find the concentration of each reactant and product at equilibrium. And to do this, you're going to use the Rice method that I spoke about. Then you divide the concentration at equilibrium by the volume of your container, and then you fill into your equilibrium constant formula, which is the Kc. So here's an example. It says 1 mole of hydrogen iodide is injected into a 1 litre flask at 450 degrees. And it says the following equilibrium was set up. It was found that 0.8 moles of hydrogen iodide were present at equilibrium. Calculate the Kc value. So let's do that. So step 1 is always to convert from grams to moles, and we've that done already from the question. The second step then is to find the concentration at equilibrium, and I said that we do that using the Rice method. So R stands for reaction, so simply fill out your reactions. We've got our hydrogen iodide, and that goes to form hydrogen gas and iodine. We know that our initial concentration of hydrogen iodide is 1 mole, and we know that at equilibrium we have 0.8 moles of hydrogen iodide. So if we can see now, if we work with the hydrogen iodide, we see that there is a change of minus 0.2 for our hydrogen iodide. So, if we look at our initial, we see that we have 1 mole of hydrogen iodide at the very start of our reaction. Now, at the start of any reaction, no products is formed. So we can say here that we have 0 and 0 for our concentrations of hydrogen and iodine at the start. We see that throughout the reaction, there is a change of minus 0.2 for our hydrogen iodide. Now, if we look carefully here, we can see that this is a 2:1:1 ratio. So any change that happens to your hydrogen iodide, there will only be half of that change for your hydrogen and your iodine, because they're a 2:1 ratio. So if the concentration of our hydrogen iodide goes down by 0.2 moles, we can say that the concentration of the hydrogen goes up by 0.1 and the concentration of the iodine goes up by 0.1. Now, I know that these are 0.1 because it's a 2:1 ratio, so the concentration here is half of the loss of concentration of the hydrogen iodide, and I know that it's a positive value because the product is being produced. So that means at equilibrium we have 0.1 moles of our hydrogen and 0.1 moles of our iodine. Step 3 then is to do your equilibrium concentration and divide it by the volume. So I would have 0.8 divided by 1, because it's a 1 litre flask, 0.1 divided by 1, and 0.1 divided by 1. So that means I end up with the concentration of hydrogen iodide at equilibrium to be 0.8, the concentration of the iodine to be 0.1 and the concentration of the hydrogen to be 0.1. So step 4 is to fill into your Kc. So I always write out the general term first. So we know that the products go on top, so it'll be H2 to the power of 1 and I2 to the power of 1 all over Hi, and that's going to be to the power of 2, and the reason that's to the power of 2 is because the coefficient in front of Hi in our equilibrium equation is 2. So I know that the square brackets indicates concentration in moles per litre, and this here is concentration in moles per litre because I divided by my volume. So I know that the concentration of the hydrogen is 0.1, and I know that the concentration of the iodine is 0.1, and I know that the concentration of the hydrogen iodide is 0.8, and that's to the power of 2. So once you get that far, you can just simply fill into your calculator to get your answer. So when we fill it in, we get an answer of 0.01562. So that means that the Kc value is significantly less than 1, so therefore the reverse reaction is favoured. Now you don't have to include that at the end, that's just me explaining it there to you. The second type of calculation that you can do is to calculate the concentration of your reactants and products when you are given your equilibrium constant. So the steps for that are to let X be the number of moles of the first reactant that must react to get to equilibrium. Then find the concentration of each reactant and product at equilibrium in terms of X. Fill into the equilibrium constant formula and let this equal to the Kc value that was given in the question, and then find the value of X and use it then to find the actual concentrations of the reactants and products. So that sounds complicated, but it's not really, so let's try an example. So the question here says the value of Kc for the reaction of hydrogen and iodine to produce hydrogen iodide is 50 at 450 degrees Celsius. Calculate the final concentration of each species if 1 mole of hydrogen and 1 mole of iodine come to equilibrium at 450 degrees in a 1 litre flask. So to solve this problem, the easiest thing would be to put step 1 and 2 together and go straight in to rice, because step 1 is clearly, it's just an explanation step really. So if I go into rice, R-I-C-E, I know R stands for my reaction, so I write it out, H2, I2, and that goes to 2HI. Now before I go any further, I'm going to indicate that this is a 1:1:2 ratio. So it tells us that the initial concentration of our hydrogen is 1 mole and that the initial concentration of our iodine is 1 mole. Now we know that at the start of a reaction, no product has formed, so the initial concentration of our product would be 0. Now, at this point is where we start to introduce X. So we know that in a reaction, the concentration of our reactants is going to decrease. So we've said that we label X as the number of moles of reactant that must react. So that means the concentration of the hydrogen will go down by X, and the concentration of the iodine will go down by X. So consequently, that must mean that the concentration of the hydrogen iodide, or the HI, must go up by a factor of X. But because it's a 1:1:2 ratio, the concentration of the HI will increase twice as much. So it will go up by 2X, and that 2 is coming from the coefficient in front of the HI. So that means at equilibrium for hydrogen we have 1 minus X, for iodine it's 1 minus X, and for hydrogen iodide it's plus 2X. So that's perfectly fine. But we must remember that we have to divide by our volume. So that's 1 minus X over 1, 1 minus X over 1, and 2X over 1. So that means at equilibrium, the concentration of hydrogen is 1 minus X, the concentration of iodine is 1 minus X, and the concentration of HI is 2X. So step 3 is to fill into the equilibrium constant formula. So I know that Kc will be the concentration of the products, which is Hi to the power of 2, over the concentration of the reactants, which is H2 to the power of 1, and I2 to the power of 1. Now, I know that my concentration in moles per litre of my HI is 2X, so that gives me that X, and the concentration of I2 is 1 minus X. And I'm supposed to let that equal to the value of the equilibrium constant, which is 50. So I know that 50 equals 2x squared over 1 minus x and multiplied by 1 minus x. So that's step 3 completed. So let's move on to step 4. So for step 4 now, we know that we have 50 equals 2x to be squared over 1 minus x by 1 minus x. So we want to solve for x. So the first thing you should do is get rid of the bottom of your fraction. So multiply both sides by 1 minus x by 1 minus x. And that leaves me with 50 by 1 minus x by 1 minus x equals 2x all to be squared. So the easiest way to multiply this 1 minus x by 1 minus x would be to use the array model. So 1 by 1 is 1, minus 1 by x is minus x, minus x by 1 is minus x, and minus by minus is plus, x by x is x squared. So that leaves me with 50 into x squared minus 2x plus 1, and that's equal to, if we square the 2x squared, you get 4x squared. So the next thing to do would be to multiply in your 50, and by multiplying in your 50, you get 50x squared minus 100x plus 50, and that's equal to 4x squared. So you want to get this 4x squared and bring it over, because you want it to be equal to 0, so you can solve it as a quadratic. So that will give you 46x squared minus 100x plus 50, and that's equal to 0. So the next thing you should do is you should do the minus b formula on that, and that will give you two values for x. It will give you x is equal to 1.39, or it's equal to 0.78. Now, we know that x cannot be equal to 1.39 because our change in concentration cannot be bigger than 1 because all we have at the start, our initial concentration, is 1 mole of each of our reactants. So your change cannot be bigger than 1. So that will mean that x is equal to 0.78. But that is not the question complete at this point, because what they've asked you to do is they've asked you to calculate the final concentration of each species. So what you need to do is you need to find now the concentration of your H2, your I2, and your 2HI. So we know that H2 at equilibrium is 1 minus x, so that will be 1 minus 0.78, and we know that 1 minus 0.78 is 0.22. It's the exact same for your I2, 1 minus 0.78, which is 0.22. And then for your HI, it's 2x, so that's 2 by 0.78, which is 1.56. So these are your final answers now for H2, for I2, and for 2HI. That's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.